PROLIM PLM.
Hello everyone, my name is Kyle Bentley. I'm an application engineer with PROLIM PLM. I'd like to thank you for joining our Lunch Bite series. For the next 30 minutes or so in this Lunch Bite, we're going to be looking at the design for additive manufacturing. In particular, we're going to be looking at the design aspect and how we can make it more efficient to help design for additive manufacturing inside of NX. So first and foremost, we need to go ahead and look at what is additive manufacturing. Additive manufacturing is referred to as 3D printing in the industry. This refers to a process used to create a three-dimensional part where layers of material are fused, formed, with a variety of techniques and methods to create an object. These parts can be of almost any shape, which cannot be machined with our traditional methods that we have, such as with our CNC machines. So here in the bottom you'll see a picture of kind of the conventional in the bottom left, and then on the bottom right is kind of what we're looking to have with the tools inside of NX to help design that kind of structure, or the additive or the 3D printed part is what we need to design for. So this helps reduce our material, helps reduce the steps, the setups for tooling. Maybe it helps reduce time of machining as well. So design for additive manufacturing inside of NX, referred to, you're going to see from the Siemens side, referred to as DFAM or DFAM. Okay, so on the bottom here you'll see optimized to print, kind of the thought process of what we're looking for. Your traditional design is the first picture there in the bottom in green. What we're going to have based on our material properties, loads, and constraints. We're going to have an optimized part that we could 3D print out in the field or in the shop. But first, then we have some validation tools to make sure that part meets our design requirements, and then we could 3D print it. Okay, so kind of the process and what it looks like there. The scan to print part, maybe we had a part out in the shop that's old, we don't have a print for it. You could scan it in, import it into NX, and then you could modify it, maybe make a better form of that part. Again, we can simulate or validate it, make sure that it meets our design requirements, and then 3D print it. So the agenda for the design for additive manufacturing tools inside of NX that we're going to be looking at is generative design, and I'll kind of explain what that is here in a second. Look at the topology optimization. We'll be looking at convergent modeling, lattice structures, and the additive validation tools that we have to make sure our design can be 3D printed here. So generative design is a process that determines the most efficient shape based on the design engineer's defined material, constraints, and stresses. So generative design is also referred to as topology optimization. So we can achieve the most efficient shape based on the designer's specified materials. So we have a tool inside of NX called Topology Optimization, and all of these tools are inside of NX CAD. Okay, so we're going to be looking at an example of that here in a second. The optimized model can then be refined or edited with convergent modeling, which we'll see here in just a second. So let's go ahead and look at a demonstration of how topology optimization works. So I have a part pulled up here, and it's a fairly simple part. So we got some geometry, maybe a couple blocks, some holes, some other geometry in there as well. Now notice I have something called a design space. So that's going to be the part where the volume of that part is consisted of. So inside of NX, we have a tab called Topology Optimization. So my part is going to be inside my design space that I have modeled there in gray. The geometry in orange, maybe I have a part that goes through there that I want to keep out. So I modeled a keep out region in blue that is also a keep out. Maybe the two holes there that you see, those are maybe some pins that I have in my design as well. So I'm going to go ahead and go to the Topology Optimization tab, and then we're going to look at setting up our optimization. So the first thing I need to do is specify where my part consists of, or the design space. So I already have that modeled. If you didn't, you'd have to go ahead and model that. So I'm going to go ahead and select it and then specify it as the design space. Now in here, notice I already have a material applied. So the Topology Optimization already recognizes if you have a material applied from NX. Okay, so it's going to be using the modulus of elasticity, ultimate tensile strength, things like that to optimize our part based on our loads and constraints as well. So the next thing I need to do is go ahead and manage our constraints in here. So I only designed half this this geometry, and I want it to be symmetric. So I can do that with the constraints. I can say planar symmetry in here. And then I can specify the face to make it symmetric about. So it's going to be symmetrical across that plane there. All right, the next thing I'm going to go ahead and do is manage the optimization features in here as well. So what these are going to be is the maybe the pins that I have for the holes. I need to go ahead and add those to my design so it knows where to optimize around. So I'm going to go ahead and hit Add All Auto Recognize Features. What that does is it looks for any features inside of NX that's in your design space specifically, such as those holes that it found. But it did not find the other two because it's not a feature that's on that body. It's physically just modeled through it. So I need to go ahead and add those manually. And you can do that with the Add New Set. So I'll go ahead and add those bodies in. Now I need to go ahead and specify the types of constraints on those. So with the simple hole 2, it's going to be a symmetrical part. I want that to be fixed in the center. So I'm going to go ahead and fix that. Maybe that's my fixed pin in my assembly design. I need it to be fixed there. The next thing I'm going to go ahead and do here is the next hole on both sides. Again, it's symmetrical. I want the load to be applied to that, which we'll do in just a second. The type of constraint, I'm going to leave it on no constraint. Now notice we could do pin, linear slide, or planar slide. Now the reason I'm leaving it on no constraint is you can have it in the degrees of freedom of rotational and translational. So it can then move freely about the translation and rotation. So I want it to do that in my design. I have a load that's going to be going in the negative Z direction. Next thing I need to do is go ahead and specify an offset thickness off of that hole. So that's where maybe that pin on my design part, maybe that's the thickness of that there. I'm going to do that for both the center and the two pins on the outside. A couple other things I'm going to point out here. Maybe for like extrude 4, notice you could do a shell. That's my keep out areas. My part's going to go around the geometry I have modeled. And that's why I added those in. So I want to specify where the part, my optimized part, is going to go around because I have parts in an assembly that represent that body there. So I'm going to leave those on keep out. And then I'm going to go ahead and accept that. The last thing I need to do is go ahead and specify my load. And I'm going to go ahead and specify it on that pin or that simple hole 3 there. It's going to be a force. And again, we can change our units here. I'm going to go ahead and leave it on pounds force and then I'm going to go ahead and specify it as, let's say, 224 pounds, about 1,000 newtons or so. And then I'm going to go ahead and select it in the negative Z direction. Then I'm going to go ahead and accept those. So I have my material applied to my design part. I have my features that I want my part to be consisted of. Now I need to go ahead and optimize that. So I'm going to go ahead and set up the optimization. Okay, from here I'm going to go ahead and select the estimate optimization based on the parameters I already have set. Now with this slider bar, you're going to notice it says fast / coarse or slow and fine. So if you want the optimization to be a little faster and not as exact in the case that it might remove more material, you could leave it more towards the left. If you slide it more towards the right, notice the minimum geometry size is going down. So I'm going to go ahead and, for this example, for the demonstration case, leave it more towards the left side, and then we can specify a mass target for our optimized part. So I'll go ahead and do that now, and then run our optimization. Now when we run the optimization and it's finished, you'll notice that it creates a facet body inside of NX. So that could be, like an STL that most people are familiar with importing into NX. When we first seen it inside of NX 11, we could use Convergent Modeling to edit a facet body or facet faces. Now with NX 12, we have more facet modeling tools to help with the Convergent Modeling to edit that body. So the optimization is meshing here in the status, and now it says it's finished. So I'll go ahead and press OK on that. Now notice my body is symmetrical, so I only drew half of it, and then I have the bodies that are kept out or keep out areas. You could also specify an offset for that. Notice I have an offset in here of 0.5 millimeter. Okay, and then the pin. So notice I modeled the pin in there as well on the back side. So that's where it represents in my assembly. I have my loads. So now we have some verification or validation to do for our max displacement. Again, we can look at that. We have our maximum displacement, and we can determine if we need a new material or if we need more thickness on those pins there. The max stress, we could look at that as well. Okay, so we can see if it's going to shear anywhere based on our material properties. So I'll go ahead and close that. Alright, notice under non-timestamp geometry you have your results for displacement and stress, and you also have your topology. Now notice that is your facet or your STL part. So inside of NX, we could then use our Convergent Modeling to edit this, which is what we're going to be looking at here in just a second. So Convergent Modeling that I've mentioned a couple times was introduced inside of NX 11. This allows the designer to work with facets or surfaces and solids directly inside of NX without any reverse engineering workflow. So we can also use the Convergent Modeling on the Topology Optimization model, since it creates a facet. And the reason it creates a facet off of the topology is so it gets us a quick result, and it doesn't have to generate analytical geometry, and it doesn't take as long. So we can then edit our topology model with Convergent Modeling. So let's go ahead and look at a couple examples with the Convergent Modeling tools here. So I'm going to go ahead and pull up the part. I have a different model that I've already performed the topology on in here. So notice I have a couple different results. I ran the topology a couple times based on maybe I needed to change the thickness of an area, or maybe I changed the material as well. Okay, so I looked at a couple different validations there. Now I have my model that I want. So let's look at editing that. So we're going to go to the reverse engineering tab here. And inside of NX 11, this was introduced to edit the facet geometry. Now notice if I go up to, let's say, the different commands we have to edit the facet, let's say I want to do a create transition, or kind of similar to an edge blend. Notice I'm not able to select anything on the facet just yet. So this is an STL or a facet geometry. I need to convert it to a convergent body. So I'm going to use the convert facet body command that was introduced in NX 11. Select it, and it'll convert it to a convergent body in my part navigator over here on the left. So you'll see that there. It is now a convergent body. Alright, so let's go ahead and look at a couple things with editing that. So some new tools that they added in NX 12, such as create transition, local offset, merge facet faces. We're going to look at a couple examples of those. So we're going to go to create transition. So notice we have round and flat. So this is something similar to edge blend inside of NX, but you can't use the modeling because it's not analytical geometry. It's actually facets. Okay, so we're physically editing an STL file inside of NX here. So maybe I want it to be a round, and I want to round off this corner here. So notice once I select it, it's going to give me an error, and it's going to say one or more bodies or facets have been found. Okay, so we don't want that. So I'm going to go ahead and hit cancel. With our optimization, it probably optimized different pieces of the model. So I'm going to go ahead and use the merge facet faces, a new command inside of NX 12. So when I select it, notice that there are different faces in here. So I'm going to go ahead and select one face, and then Windows select the rest to merge all of those together. Okay, then we're going to go ahead and rerun the create transition. So I can go ahead and specify maybe a round or edge blend that corner off of there. And I can simply do that by just selecting points on the vertex. Now notice if it was a closed loop, we can do that. So I can go ahead and specify it as closed, since this is going to be a closed loop. And as you specify more points and going around the facet, it's going to automatically infer that for you. So maybe I select over here on the left here, on that vertex. Now notice if you miss it, that's okay. You could also move it. You can delete the point. You can do different things with those. Okay, so notice as I move that point and select it, that it physically infers it all the way around that edge. So I'm going to specify it as 1 millimeter and then press OK. So notice we used a create transition. We did an edge blend on a facet body. So the reason we did a merge facets as well is that could cause problems later with editing. Obviously we got an error there, and it could also cause problems later on with when we 3D print the parts. It's, you know, separate facets, it's separate bodies in there. So maybe we need to look at a tool to validate that our facet is good enough or it meets the requirements to 3D print. So there's something called cleanup facet body inside of NX 12. So I'm going to go ahead and run that here. So we're going to go ahead and select our body. Now notice there's all to analyze or all to repair. So I want to go ahead and analyze those facet faces. I'm going to go ahead and just use all of those here and then click show the results. Now notice there's one intersection face and 623 degenerated facets in here as well. And what those could be is facets that need to be modified, and it would be up to the designer to kind of modify those as he needed. So there's also an intersection face or facet, excuse me, in here as well, and you'll notice that it's actually kind of bad. Okay, so they intersect those two. So with 3D printing, you know, that's an area that might need to be fixed. Okay, and it would be up to the designer if we didn't have this tool to find those areas manually. So with this tool, what's really nice, it doesn't just analyze it, we can also repair it on the fly. So I can say repair all of those for me, and then click show the results. So it'll go ahead and repair that intersection facet that I just showed you there, and the degenerated facets, it'll go ahead and modify those as needed to the body. So notice we have a good enough body here. There's no errors, there's no intersections, there's no slits in those facets, nothing like that. So we can go ahead and press OK. So that's a really nice tool to validate your facet body. A couple other things we're going to look at that are new inside of NX12 is the local offset command. Notice here I already have a part or an STL that's been imported. Notice I have the convergent body. I already ran the convergent facet, did some trimming to this model. Maybe I have to design a hood scoop on this. Okay, so this is my my facet model. So I'm not going to use the traditional modeling commands. However, you could, or you could use the facet body operations in here. So with NX12, they added a new command called local offset. Okay, so I'll go ahead and run that. So with local offset, I'm going to go ahead and use the single facet region in here. So I'm going to go ahead and window select and draw maybe, a hood scoop in here. And it'll preview, and we can do the offset distance up. Maybe I specify it as 10 millimeters. Another thing that's really nice is the transition. Notice that it's really sharp in here right now. I could specify it as a constant offset or a smooth radius, if you will. Okay, so I can specify that. And then we could quickly modify our facet with that command. So we quickly generated maybe our quick hood scoop in there. Okay, so that's how we can use convergent modeling to edit our facet geometry. Okay, so we can use the topology part. Notice here as well, maybe you have in your brace in the bone, in this case in the picture in green, I have modeled a brace for the medical industry on somebody's kneecap that they need to do surgery on and slice off there. I need to take and import that person's bone to fit it. So I already had my my brace modeled, and I just need to subtract it. So you can use traditional modeling commands, or you can use the facet body operations as well. Okay, so we can use that on our topology models, or you can import scanned models as well. The next thing we're going to be looking at for DFAM, or design for additive manufacturing, is lattices. So you're going to see these lattice structures. They're becoming more common in the industry. So these structures help reduce costs, keep the part lightweight, keep the structural integrity and strength, and can even improve part efficiency in cases such as this turbine blade over here on the right. You'll notice that the area of the airfoil shape is voided out, and we have the lattice structures in there to help with the cooling efficiency of that. Okay, so I'll go ahead and show you that that example here. All right, so I'm going to go ahead and pull up that turbine blade. Now notice in here I have the area in red is the volume that I want the lattices to be consisted of. So inside of NX, we can quickly create those complex lattice structures in just seconds with the lattice structures command. So I'm going to go ahead and go to the lattice command here. And then I'm going to go ahead and use the type as unit graph. And this was introduced in 1102. So we could use the unit graph. Inside of NX12, we have one conformal graph as well. I'll show you an example of that here in a second. So with unit graph, it says select body or the volume structure of that. So I'm going to go ahead and select that volume of where I want those lattices to be consisted of. So I'm going to go ahead and leave it on the bi-triangle here. You can specify different ones in here. The edge length I'm going to leave as 3 and the rod diameter. And then I'm going to go ahead and show those results. So what's nice about the lattice command is it generates those complex structures and not just an analytical shape. It creates it in a facet body so it can quickly generate and quickly be edited if need be inside of NX. So I can go ahead and accept that. And then I'll go ahead and hide the body that I have, or the volume, to be consisted of those lattices. And you can see the lattices are then put into that volume. Okay, so we have the lattices inside of our airfoil shape to help with the cooling efficiency inside our gas turbine engine here. All right, another example we're going to look at is the conformal lattice structure here. So I'm going to go back to the lattice command. We're going to look at the other type is the conformal graph. So notice this one says the select face. Okay, so with the conformal graph and how that works is it's going to take the shape. So notice I have a surface in this body in here in the darker gray that I want it to conform around, all right, or design around it. So I'm going to go ahead and select that face there. So it's going to go ahead and select it all the way down based on my face rule selection of tangent. All right, now I'll go ahead and specify the edge length and the rod diameter. So we can also specify an offset, and I have that specified as -3 in there to offset it right in the center of my surface here. And you'll see that here in just a second. So those lattices are going to take the curvature of that surface in there. So again, it's going to generate the facet body that we can quickly edit if we need to. Once that gets generated, you're going to see that the lattices are then conformal with that surface. So you can see that there. So let's go ahead and look at a unit graph on this body. So I have a body that's already in here. Let's look at what the unit graph looks like compared to the conformal. So let's go ahead and run the lattice command and then run the unit graph versus the conformal. So I'm going to go ahead and leave the options in here as 6 and 1. Notice it's the solid body or the volume I want it to be consisted of. So I'm going to go ahead and select that. And then I'm going to go ahead and preview those results. So that's going to generate my facet body. You're going to see that it's a unit graph and it doesn't take the curvature of that surface there. So once that gets generated, we can go ahead and press OK on that. Notice it quickly generates that. It's not an analytical shape. Notice it's not taking the curvature of it. It's more of a linear shape in here. And you can see that as I rotate and snap to the view, it's more linear than it is conformal. So you can see the difference between those two there. As I unsuppress that, you're going to see that it's going to go ahead and regenerate it. So notice the conformal takes the shape of that versus the linear or the unit graph, if you will. Okay, so that's the two differences. Again, the conformal was added inside of NX12. So notice that's more of a linear shape there. Okay, a couple other things that we're going to look at here are our validation tools for additive or 3D printing as well. So we're going to look at the wall thickness, overhang angle, printable volume, and a tool called wholly enclosed volume. Alright, so I'm going to go ahead and pull up this part here. So the reason they have these tools is to validate that your part can be 3D printed. So I'm going to go ahead and go to the Analysis tab. So they added a group inside of NX called Design Validation for Additive Manufacturing. So we have different ones such as wall thickness, overhang angle, printable volume, and wholly enclosed volume. So the first one we're going to look at is the wall thickness. So this command wants us to select the body. So we simply select the body and then specify the coordinate system. So it's based on the z-axis. So what I'm going to do is go ahead and snap it to the center. Specify a minimum thickness. This part's in millimeters here, so 1 millimeter. I'm going to go ahead and leave less than the minimum thickness I have specified in red, and only show the minimum, less than minimum thickness on there. So I'm going to go ahead and calculate that. So notice it shows those faces that are less than a millimeter thick. So what happens with the ceases is if you have it off angle and then go ahead and calculate that, it's going to go ahead and look at that z-axis and the minimum thickness of where it is normal to that face. So it's specifying the other thicknesses now. Alright, so make sure that your coordinate system is squared up, and then you can use the wall thickness validation tool as well. A couple other things we're going to look at: printable volume, overhang angle, and wholly enclosed volume here. So the first one we're going to look at here is the, let's look at printable volume. So we have a printable volume, and what that is the volume display of, let's say, the product. So it's going to give us the bounding block between that. So we could say it's a block or a cylinder in there. So it'll give us the volume of our product. The next thing you can specify is the printer volume. So you can specify this on your own. You could say it's a block size. This is the volume that the printer consists of here. And then we could say, hey, I want to look at both of those together to make sure my part can fit inside my printer. So we can use the check printable volume to check to make sure our product will fit inside of our 3D printer. Another check we're going to look at here is the overhang angle. So again, it's going to go ahead and select the body. I'm going to specify the build plane. Now notice with the check overhang angle, it's using the z-axis again as well. So this one will be dynamic. I'll show you this one in a second. There's no calculate button. So maximum overhang angle, anything over 45 degrees normal to the z vector, it's going to find. So as I rotate this, you'll notice that the faces change. Again, it's based off the z vector there. Couple other things we're going to look at is they added a command called wholly enclosed volume. So what this would be used for is more of your powder bed fusion checks. Notice as I ran that, it failed. So if you use more of a powder bed fusion 3D printer, then you would probably use this. You want a void in your part to so the powder can be emptied from the part once it's 3D printed. Okay, so that's not for your metal extrusion, that's more for the powder bed fusion as well. So notice it failed this check. I'll go ahead and close that. Maybe I need to go ahead and put a cutout in here. I'll just go ahead and suppress that. Notice I already had a sketch and that built in my part. Okay, so it goes ahead and puts that hole that I already have modeled in there. Notice it's shelled out in there, so there's a hole physically in this shelled area. So as I run that wholly enclosed volume, it'll go ahead and pass it now. So once I 3D print that, I could empty the powder from my part. Okay, so that would be used for more of your powder bed again. Okay, so they added that command and our different validation tools that we have as well. Alright, that's all I have for design for additive manufacturing inside of NX. Some of our other upcoming lunch bites that you're going to see, some of our NX lunch bites, the NX CAD animation designer. the NX CAD, the new functionality with hole making. In NX CMM, we're going to be looking at using or how to use the NX CMM product inside of the NX environment there. Some other Solid Edge lunch bites that we're going to have is what's new in Solid Edge 2019 Part 2 coming up, and Solid Edge Electrical. Again, thank you for attending this lunch bite. If you guys have any questions or concerns on design for additive manufacturing or further lunch bite suggestions, please email those to our engineering support team at technical.support@prolim.com. Thanks, and have a great day.
PROLIM PLM.